Good evening, everyone. This is the last summary session of the NPTEL course, Basic Electrical Circuits. And today I'll summarize what we have discussed in these 12-week sessions. Let me share my screen. So now I'll be summarizing what all we have discussed during these 12-week sessions. So I'll just go through my notes, and then after summarizing all the content that we have discussed, I can address your queries as well as doubts if you have any. So in the week one, we have started with the basic introduction about electrical circuits, and we have discussed about the terminology like water elements, water sources, and then we have also discussed about KCL. So KCL is Kirchhoff's current law, which will be applied at a node, and then KVL is Kirchhoff's voltage law, which will be applied in a loop. And we have also discussed the polarity and how we will get the KVL equation as well as KCL equation, and then we have discussed about voltage sources, current sources, water ideal voltage source, water ideal current source. But in practical, none of them are ideal. There will be some parasitic resistance in series with the voltage source, and there will be a resistance, high resistance in parallel with the current source. But here we have discussed about normal ideal voltage source, and for ideal voltage source, or we can consider it as a battery, which is a large capacitor. Current source, practically it will be either a large inductor, or if it is MOSFET level, we can consider MOSFETs some kind of circuit that will act like a current source. And then we have also seen that voltage source cannot be short circuited. Similarly, current source cannot be open circuited, because in one case KVL will fail, in the other case KCL will fail. And then we have discussed about basic elements, which are resistor, capacitor, as well as inductor. And we have seen resistor is memoryless, and capacitor and inductor they have memory. And then we have also discussed about mutual inductor, which is a very important topic. And then we have seen that there is something called dot polarity, and we have also seen that if the currents are entering the dots in both the cases, and if the mutual inductance is M, then we'll have a plus sign, something like this. So here the voltage induced across this coil will have two terms. One is because of the self-inductance, and one is because of the mutual inductance. Self-inductance and the current flowing through that coil will give the first term, and the mutual inductance will cause because of the current flowing in the other coil. If the current is entering one dot and leaving the other dot, then we'll have minus sign here because of the mutual inductance. And these are very simple and straightforward, but you should not make any mistake while solving the problems. Then we have seen assignment, few assignment problems. Here, maybe I'll go a little bit faster. We have seen that in the first question, we have to apply basic KCL, and then we'll get the current. And in the second question, you have to apply basic KVL, and then you will get what is the V1 voltage. And here they have given IV graph, and they're asking resistance. So we know that resistance is voltage by current. So voltage is minus 3V and current is minus 150 microampere. If you see resistor, if the voltage is positive, current is positive, voltage is negative, current is negative. So that's why the graph will be always in first and third quadrant, not other quadrants. And also, we have also seen that if they have given current waveforms or voltage waveforms, how to calculate voltage and corresponding current. Yesterday also we have discussed the same. So whenever they give any such waveform, first you have to write the expression. So for given circuit, say for this kind of circuit, what is VC? We know that I is equals to C into dV by dt. So current entering the capacitor will be I1 plus I2. And now we know that V is 1 by C integral I dt. So basically voltage is nothing but integration of summation of both the currents. So I can separate it out and write integration of the first current plus integration of the second current, which is area under the curve. So I can directly calculate the area, and then I can add it up and then divide by the capacitance to get the voltage. So these problems are pretty much straightforward and easy. So we have also seen similar kind of problem in yesterday's session, where we have to calculate the voltage. So first you have to write the expression for voltage. V is equal to LdI by dt plus 1 by C integral I dt. We have to write it in terms of I, because they have given the waveform or the graph of I. So once you do that, then you can calculate directly. This is very simple. We have to find the slope here, and this is the integration of the current, so which is the area under the curve. So this is also something similar. So all these we have seen that they are very simple and straightforward. Here we have infinite series, and you have to get in terms of an infinite series. So a plus a plus a square plus up to so on infinity is nothing but a by 1 minus. So this is all about week one, where we have discussed a preliminary concepts like KCL, KVL, and then we have discussed about elements like RLC, and then voltage and current relationship of those elements, voltage source, current source, etc. In the week two, we have discussed about a series connection of voltage sources, and then parallel connection of series connection of current sources. If you connect voltage source in series, the overall effective voltage will be summation of the voltages. But current source, you need not, you should not connect in series, because until and unless they are equal, KCL will be violated. So if at all they are equal, then there is no issue. But if they are not equal, then KCL will be violated. So while connecting current source, we should be very careful. Similarly, if the resistors are connected in series, summation, the effective resistance will be summation of the resistances. Capacitor, it will be the inverse. So the inverse of the effective capacitance will be the summation of the inverse of the individual capacitances. And inductance is again similar to the resistance. Effective inductance will be summation of the individual inductances. So these are all the series connection of the elements. Now coming to parallel connection, what is the series connection of current source is same as the parallel connection of voltage source. If the voltages are not equal, then KVL will be violated. So voltage sources should not be connected in parallel if they are not equal. Current sources, if they are connected in parallel, then the effective current source will be the summation of these individual current sources. Similarly, if the resistors are connected in parallel, the inverse of the effective resistance will be the summation of the inverse of individual resistances. In capacitance, the effective capacitance will be the summation of the individual capacitances. And inductor will be same as the resistance. So the effective inverse of the effective inductance will be the inverse of the the inverse of the effective inductance will be the summation of the inverse of the individual inductance. And this I have explicitly mentioned because there are many problems which are dependent on this. So if we have infinite series, say geometric progression in infinite series, a plus ar plus ar square up to on infinite, and if r is less than 1, then the infinite summation series can be written as a by 1 minus l, so which might be used in few of the problems. So that's why I have explicitly mentioned. Then in this week, we have studied about control sources, different control sources like voltage control voltage source, voltage control current source, current control voltage source, current control current source. And we have seen the diagrams of these voltage sources. If it is voltage control voltage source, the gain is dimensionless. If it is voltage control current source, the gain, it has the dimension of transconductance. If it is current control voltage source, it has the dimension of trans resistance. If it is current control current source, it is again dimensionless. And then we have solved a few problems related to different network of resistance connected in series and parallel. And it is very simple. You have to find the effective resistance and calculate. Here also they have dependent sources. So if it is dependent source, it is depending on some other voltage or current. Accordingly, you have to consider the voltages and currents and apply KCL and KVL, and we have to solve. And these are also very simple and straightforward. But only thing you have to be very careful is whenever there is any dependent voltage source or dependent current source, while applying Thevenin's theorem, while applying superposition theorem, you have to be very careful because it is dependent on some other current source. So you have to be very careful while applying superposition theorem. So after that, we have solved similar kind of problems on all dependent sources. So in this week, I have covered many problems where I have touched upon all 4 dependent sources, so that we'll be confident about it. Similarly, we have considered many different circuits where they are asking, if you see, like here they have resistive network and they're asking V not and I not. So here we have applied basic KVL and KCL and we have solved for the same. And then this is another voltage control current source example. And here also we have applied basic KVL and KCL. So all these circuits can be solved by applying basic KVL and KCL, but only thing we have to be careful with the voltage polarity and how this voltage or current is dependent on another voltage or current. Accordingly, we have to apply KVL and KCL and we can solve it easily. So until this point, do you have any doubts?
Sir.
So in week 3, then we have moved into power and energy in the circuit element. So we have seen that if power is positive, then it is absorbing power. If power is negative, then it is delivering the power. And then we have seen that energy is nothing but integration of the power. Then we have seen the power and energy in a resistor. Power is voltage into current. So for a resistor, it is I square R or V square by R or V into I. And energy will be integration of the power, and it is coming greater than 0. So that's why it is passive element. And as we have discussed, resistor can only absorb energy and it will be dissipated as a heat. So power is positive, and that's why if you see as IV characteristics lie in first and third quadrants, power is always positive. It always absorbs power. And in the case of capacitor, if you calculate, if we'll get as V of t into I of t, and I is nothing but C dV by dt. So power is C into V of t into dV by dt. So now we have considered four different cases where V of t is V of t and dV of t by dt are positive and negative. So there are two terms, and each term could be positive or negative. So we'll get four such oral case studies. So sometimes it is absorbing power, sometimes it is delivering power. But if you see energy, energy is always positive, and that's why it is also passive element. So capacitor can store the energy, and while storing, it is absorbing the power, and sometimes it can deliver the power also. So if you consider any circuit with voltage source, resistor, and capacitor, initially capacitor might be charged with the voltage source, and if the voltage source is shorted, then capacitor will dissipate by giving the power to the resistor. So capacitor can absorb the power and deliver the power. Similarly, inductor also will get four such cases where it can absorb power or it can deliver the power. But energy again, here it is half L square and here it is half CV square. So energy is coming to be greater than zero. So it is also passive. So that's what we have finally defined. If the energy is uh, can be positive or negative, then it is an active element. If the energy is always positive, then it's a passive element. And if the power is positive, it is absorbing power. If the power is less than zero, it is delivering power. Voltage source, it can take the current or it can deliver the current. So I can be positive or it can be negative. So energy can be positive or negative. So it can deliver energy or it can absorb energy. So that's why it is active element. Similarly, current source can also absorb energy or it can deliver energy. So that's why it is called active element. Then we have seen the circuit analysis. So when we are discussing about circuit analysis, we have generalized the discussion by saying we are considering circuit with N nodes and B branches. So in this circuit also we have considered say N nodes, but here we have four nodes, and say B branches. Here we have eight branches. So in a circuit, when we are trying to solve, we are trying to solve voltage of each and every branch and current through each and every branch. So we need two B quantities. So if there are B branches, we want B currents as well as B voltages. So we need two B variables. We want to find out two B variables, which means we need two B independent equations. So we have seen that if you apply KCL at every node, as there are n nodes, we'll get n minus 1 independent equations because the other equation will be dependent. So we have n minus 1 independent equations. And if you apply KVL in each and every loop, we'll get b minus n minus 1. How we got these many equations, that it is explained in the second upcoming slides. So this will give me b minus n minus 1. And if you apply IV characteristics of each branch, it will be b because there are b branches. So now if you add it, we'll get two b equations. So KVL at each node, if you apply, you will get n minus 1 independent equations. Now if you think about KVL in each and every loop, then you will get b minus n minus 1. But how do we know how many KVL we need to apply? So that's when we started discussing about graph, and then we started discussing about tree. Tree is nothing but it's a set of branches which covers or which traverses through all the nodes without forming a loop. So in this case, there may be different trees: 1 to 2, 2 to 4, 4 to 3, or 1 to 4, 4 to 2, 2 to 3. But here we have considered one such tree, which is traversing from 1 to 2, 2 to 4, and then 4 to 3. So if you form a tree, then co-tree is nothing but the other elements which are not part of the tree. Now, if you consider tree plus any one element of the co-tree, then it will form a loop. So now what happens? Number of loops is how many such loops will be formed? The number of loops that can be formed is number of branches in a co-tree, because if you consider any branch of a co-tree, it is forming a loop. So the number of loops that can be formed is the number of branches in the co-tree. So how can I find the number of branches in the co-tree? It is the total number of elements B minus number of the branches in a, the total number of elements in the given circuit minus the number of elements in a tree. Or I can say the total number of branches B minus the number of branches in a tree. Because there are n nodes, the branches in a tree will be n minus 1. So B minus n minus 1 is the number of branches in a code tree, which is also equal to number of loops. So the number of KVL equations that we will be getting is B minus n minus 1. So by applying KCL, you will get n minus 1 equation. By applying KVL, you will get b minus n minus 1 equations. And by applying IV characteristics, you will get b. So total, you will get 2b equations and 2b independent variables and 2b independent equations. So you can solve these equations to get the I and V for each and every branch. Then we have also discussed about superposition theorem, which is very simple. That if there are multiple sources acting together, then you can consider each source at a time, and then you can add the sum of the effects. And then we have also solved the same. We have solved a few problems on power related as well as energy related, and then for dependent sources or independent sources, what is the power delivered by the source or what is the power absorbed by the source. You have to be very careful. If they are asking power delivered and say it is absorbing, then you will get a minus sign. You have to enter minus sign in your answer. So you have to be careful whether it is delivering the power or it is absorbing the power. Also, while uh, entering the answer, you have to be sure whether it is they are asking whether the power is absorbed or delivered. If they are asking the opposite, you have to enter one minus sign and you have to be careful with it. And then here also you have seen depending upon the power, whether it is positive or negative, accordingly they are asking whether it is passive or not. So the same here in this week, we have not studied about how to solve those equations, but they are just asking how many KVL equations, how many KCL equations. So first we have identified 4 nodes and B branches are 8. So the number of KCL equations is n minus 1, which is 3. Number of KVL equations is B minus n minus 1. So 8 minus 3, which is 5. So that's all about week 3. So week 3, it is just an introduction to circuit analysis and power and energy of the elements. In week 4, we have went in detail of circuit analysis. So we have started with the basic KCL equations. So if I have a circuit with resistors and current sources, which is the easiest circuit for applying KCL. Say here in the circuit we have 4 nodes, so we'll apply KCL at 3 equations. Say the 4th node I'm considering to be ground because like I have the freedom to consider any terminal as ground unless they have given. So if in the given circuit there is no ground, I am free to assume any terminal to be ground. But if they have given a ground, we have to consider that terminal as a ground. So now, if we consider the currents in these branches, like in this direction, now we can apply KCL at node 1, KCL at node 2, KCL at node 3. You will get 3 equations in terms of impedances. Now I can write these impedances in terms of a matrix. This matrix is called conductance matrix. This is the variable vector and this is the independent source vector. Why we are getting 2 sources? Because we have only 2 sources, I1 and I3 here. Now, conductance matrix can also be written directly by looking at the circuit. How? The diagonal element is the total conductance at node I. So the total conductance at node I is G11 plus G12. And similarly, at node 2, it is G12 plus G22 plus G23. Similarly, at node 3, it is G23 plus G33. And Aij will be the negative of the conductance between node I and node J. Say I want A12. So A12 is the negative of the conductance between node 1 and node 2. It is G12, so minus G12. If there is no resistance in between 2 nodes, then conductance, there is no conductance basically because the resistance is infinite as there is no resistance connected, which means conductance is 0. So that's why we are getting 0 and 0. And on this side, it is the current entering the node. So current entering the node is I1 here, current entering the node is I3 here. If the current is leaving, then you will get a minus sign. Then this week it is all about solving the problems by getting the conductance matrix. So they have asked what is the conductance matrix, and if you see if it is resistors and current sources, it is very straightforward. You can directly write the conductance matrix, and these are currents entering the node. You have to be very careful, and these are independent. These are the independent currents. If there is dependent current source, then it will be somewhat tricky, and you have to see how you will get the equations. And this conductance matrix is very easy to get. We can directly write it by looking at the circuit itself. This is the conductance at that node. This is also conductance at that node. This is also conductance at that node. This is the conductance between those 2 nodes and multiplied by -1. So after getting this, you are asked to calculate V1 and V2 and V3. You have to do the inverse of this matrix and then you can get it. So you can see that if there is no dependent source, this will be symmetric, as I have mentioned. If there is any dependent source, then it will not be symmetric. Then we have solved different problems on the dependent source. If there is any dependent source, say here there is a dependent source here. Then what happens? The KCL at node 3 will have different expression because of this additional term that is coming because of this dependent source. So that is what is causing the conductance matrix to change. So node 1 and node 2, it is simple and straightforward, it remains the same. For node 3, you have to write the KVL equation and then you have to substitute Vx, which is V1 minus V3. After that, you will get the conductance matrix and it will not be symmetric anymore because this dependent sources is causing an additional term to come and because of which the conductance matrix changes and it is no more symmetric. And again, you have to multiply the inverse of this matrix on both the sides to get the V1, V2, and V3. So one more thing, in this type of problems, you have to be very careful while entering the matrix because they have specified a particular way using which how you have to enter the values in the given box. So you have to be very careful and you have to follow the same rules that they have mentioned below the question, else you will not get any marks. Similarly, if it is current control, current source, again, first you have to write the equations at the nodes where there is no dependent source is connected, and these are very straightforward. And at the node where there is some dependent source is connected, there you have to write the KVL and then you have to substitute this dependent current or voltage term in terms of independent voltages or node voltages. And after substituting it, you will get the conductance matrix, and by inverting it, we will get the voltages. Then we have done another critical case, which is the independent voltage source. So what is the issue when there is an independent voltage source between two nodes? Because if there is any independent voltage source between these two nodes, I cannot get the current flowing through this, right? Because I cannot apply voltage difference by current because there is no resistance in this path. How can I calculate the current through this? So we cannot directly calculate or write the conductance matrix. So what happens here is we will apply something called super node. So first of all, if there is a voltage source connected between these two nodes, I will get one equation directly. I need to get another equation which is obtained using the super node. So when you are doing super node or when you are writing the super node equation, you have to be very careful. What we do is basically we consider this as a single node. So now while applying KVL, you will apply this, you will apply KVL or sorry, you will apply KCL by considering these two nodes as a single node. But while writing the terms that are related to V2, you'll write in terms of V2, and the terms that are related to V3, you'll write in terms of V3. So basically, you will get one equation at the terminal 1 and another equation by using the independent voltage source and another equation by applying this super. So you will get basically 3 equations and 3 unknowns, and you have to solve for the same. Again, here you have to be very careful while entering the terms in the given box. And then we have dependent voltage source. So dependent voltage source also the same. You have to apply super node. But one equation you will get directly from node 1. Another equation you will get from this dependent source Vx. And another third equation you will get from the super node. So once you get all the 3 equations, you have 3 equations, 3 unknowns, you can solve it. So until this, do you have any doubts?
No.
No.
Yeah.
So in the week 5, so week 4 we have discussed about nodal analysis. In week 4 we have discussed about nodal analysis. In week 5 we have discussed about mesh analysis or loop analysis. So first we have seen that it can be applied to planar circuits only. What are planar circuits? Any circuit which can be drawn in the plane without crossing any branch. So if you cannot draw the circuit without crossing a branch, then it is not a planar circuit and you cannot apply mesh or mesh analysis. So if they have not mentioned anything, it's always easier to apply the nodal analysis, but it's up to you. If you are comfortable with the mesh analysis, you can also apply the mesh analysis. So what is mesh? Mesh is a loop in a circuit which does not enclose any other loop. So you have to consider that loop which will not enclose any loop inside it. So here if you see, this is one loop which does not enclose any other loop. So this is a mesh, this is a mesh, and this is a mesh. So 3, 4, 2, this is a mesh, but this 3, 2 outside one is not a mesh because inside it there is another loop. So that is a loop but not a mesh. So here we have 3 meshes, so we will get 3 equations. So for nodal analysis, it is easier to get the equations for a circuit with resistors and voltages. Here it is easier to get or I would say the easiest circuit to apply mesh analysis is the circuit with resistors and independent voltage sources. Also, the easiest circuit to apply nodal analysis is circuit with resistors and independent current sources. So here also we'll get some matrix called resistance matrix, and we'll get R into I is equals to V, where V is the independent voltage source vector. So how to get the resistance matrix? First of all, it is symmetric if there are no dependent sources, but if there are dependent sources in the circuit, then it will become asymmetric. And it remains the same as conductance matrix. The diagonal elements are summation of the resistance in the mesh I. There it is the summation of the inductance at node I. And Aij, here it is negative of the resistance common in mesh I and mesh J. There it is negative of the conductance in between node I and node J. So both are more or less same. And I have also given a table where you can directly get the difference between nodal analysis and mesh analysis. So here it is easier for resistors and independent current source circuits. Here it is easy for resistor and independent voltage source circuits. So in the exam, if they have given this circuit, then you have to understand that mesh analysis would be the easiest one to do. If they have not mentioned any analysis method, say they have not mentioned whether you have to solve by nodal analysis or mesh analysis, then you are free to choose any of this method, and now you know which is easier to apply for a given circuit. Accordingly, you can apply. Here, if there is any special case, which is if there is any voltage source between two nodes, then you have to apply super node. If there is any current source between these meshes, then you have to apply super mesh. And we have also discussed about a few theorems called superposition theorem, which you already know, and substitution theorem, where current source can be converted into voltage source or a resistor accordingly, which is also simple. Then we have solved a few problems where the first problem is pretty much simple and straightforward. It is resistors and voltage source circuit. So you can directly write the resistor. So in the mesh one, what is the summation that will come here? And the summation of the resistor in the mesh 2, summation of the resistor in mesh 3. And this is the negative of the resistance that is in common with the mesh 1 and mesh 2. And here there is no common resistance between mesh 1 and mesh 3, so it is 0. So once you get the matrix, and we are applying, so one thing it is very crucial, we are always applying in clockwise direction. So the voltage source, we have to always traverse in the clockwise direction. So I'm starting it here. So it is plus 3.4 and minus 13.6. That's why I got minus 10.2. In this mesh 2, it is plus 13.6 and minus 3.4. So that's why 10.2. In the third mesh, it is plus 3.4 and minus 6.8. It is minus 3.4. So you have to be very careful with these polarities. If you mess up any plus or minus n, you will end up getting a wrong answer. So you have to be very careful with these polarities minus and plus, and you should be very careful while entering this in the box as well. So once you get this equation, you have to apply the inverse of this matrix, and you can solve for I1, I2, and I3. And if there is any independent sources, say the dependent source is there in mesh 1, say here it is in both mesh 1 and mesh 2, then there will be different equation in mesh 1 and mesh 2. So you have to write the KVL equation is in mesh 1 as well as KVL equation in mesh 2, and you have to substitute this term. Here it is 1 kilo ohm into Ix. And again, what is Ix? Ix is nothing but I3 minus I2. So you have to substitute that Ix. And then mesh 3, it is normal. It is having resistors and independent voltage source. So again, now if you see, it is asymmetric because this dependent voltage source is injecting one term, which is changing the matrix. Because of that, we are getting one asymmetric matrix, and by applying the inversion of this matrix, we can get the currents. Similarly, if it is independent, so here we have considered circuit with independent current source. So if there is any independent current source between two meshes, then you cannot apply KVL because you don't know the voltage across the KVL. Similarly, you cannot get the current through the voltage source, and hence you cannot apply nodal analysis when there is voltage source. Here it is current source. But if you see, if there is any current source that is shared between two meshes, you can directly get one equation from this current source, and you can get one mesh equation from this mesh where there is no independent current source. So you will get two equations from there, and another one is the super mesh where you will apply the KVL in the outer mesh. So there is no current source. But when you are applying the super mesh in the outer loop, you have to consider this outside equation. So you will get one equation from the super mesh, one equation from the mesh 1, and another equation from this current source. So three equations, three unknowns, and you can solve for it. So that completes our week 5. So week 5 was about mesh analysis. And coming to week 6, here we have discussed about Thevenin's theorem as well as Norton's theorem. And this equation, this week is also very simple and straightforward. So in week 6, we have discussed about Thevenin's theorem. We have seen any given circuit can be written as an equivalent voltage, which is Thevenin voltage, and equivalent resistance, which is Thevenin resistance. How will we obtain Thevenin voltage, which is the voltage obtained across the open terminals 1 1 dash, and Thevenin resistance is the resistance obtained at 1 1 dash by considering all the independent sources to be zero. If there is any dependent source, we cannot neglect the dependent source. Dependent source will be as it is, but independent source we have to make it zero. Then we have considered few problems and calculated V Thevenin and R Thevenin. I'm not going in the details because the concept remains the same. So for maximum power transfer theorem, we have seen that R Thevenin and Rn should be equal, and if they are equal, then power transferred or the P max will be V Thevenin square by 4 into R Thevenin. So now Norton's theorem is the equivalent of Thevenin's theorem. In Thevenin's theorem, we have V Thevenin and R Thevenin in series. Here you will have I Norton and R Norton in parallel. So Norton current is obtained by short circuiting the terminals 1 1 dash and calculating the current through the terminals, and Norton resistance is nothing but Thevenin resistance. So it is obtained as by calculating the resistance at these two terminals by considering the independent sources to be zero, not the dependent sources. So this is the Thevenin equivalent and this is the Norton equivalent, and this is the relationship between both of them. So V Thevenin is nothing but I Norton into R Norton. So sometimes say if you cannot calculate the effective resistance between these two terminals because there is some dependent voltage source or dependent current source inside, then you excite it with some voltage V test and calculate I test. Now the Thevenin resistance will be V test by I test, which we have discussed thoroughly and solved many problems on. So there could be different circuits with different scenarios like voltage control current source, current control voltage source, but the topic or the concept remains same. First, you have to calculate, say, I Norton, then you have to short it and calculate the I Norton. R Norton, you have to excite it with some test voltage V test and calculate the I test, and then you have to do V test by I test, which will give you R Norton. Then they are asking what should be the value of the resistance so that the maximum power will be transferred. So when it will be maximum, when R load will be R Norton. So that's how you can calculate. So someone has asked how to improve ourselves. So I have just given that you have to go through the lecture videos that sir is discussing, and then you have to uh, solve with me during the problem solving session. And also I have told that if you are not able to solve, you have to see why you are not able to solve, whether there is some issue in the conceptual understanding or you are making any mistake. So first you have to identify the problem, why you are not able to score good marks. Then you have to start addressing the problem. Say if you are not conceptually clear, then you have to go through the lectures or the problem solving sessions where I have discussed the concepts. Then once you are thoroughly understood, then you have to solve uh, problems, because sometimes even if we feel like we have understood the concept, we may not be actually able to apply to the problems, because concept understanding the concept is a different thing and applying the concept is a different thing. So not only you should understand the concept, but also you should understand how to apply it to solve the problems, which is again the important thing. So you have to solve as many problems as possible. So you'll understand how to apply the concept that you have learned, and also you'll not make any mistakes and you'll feel confident. The more problems you solve, the more confident you feel. And I have told that once you solve the assignment, if you have made any mistakes, try to solve it by yourself first and see whether you can rectify your mistake. If not, then we have also explained few assignment solutions in few of our lecture videos. You can go through it and see where you have made the mistake. And we have then discussed about two-port networks. In this week, we have only discussed about biparameters, which is the relation between the currents as well as voltages. For two-port network, please be careful with the voltage and current polarities. So this is the voltage polarity and this is the current polarity. So here the input is the voltages and output is the current. So y11 is equals to I1 by V1 when VT equals to 0, and that's how these parameters are defined. And we have also solved few problems where they're asking to calculate the y parameters. And if you see, if I make v1 equals to 0, I will get two parameters, y12 and y22. And if I make v2 equals to 0, then I'll get the other two parameters. So you have to solve the circuit two times to get the parameters. So that's all about week 6. Any other queries? Until week 6, any other queries you have? Is it clear until week 6?
Yes.
Okay. So in week 7, we went in detail with the y parameters. We have discussed about y parameters, z parameters, h parameters, and g parameters. So y parameters are also called as short circuit parameters, and it is in terms of I equal to y into v. And z parameters are also called as open circuit parameters, and they are in the form v is equal to z into I. And h parameters are in the form something like this, and it is neither voltage nor current on the left side, but it's a mixture of voltage and current. So we have V1 and I2 as the output, and I1 and V2 are the input, and these are the H parameters. Kindly also check the dimension of these H parameters, Y parameters, and uh, Z parameters. So they are not having the same dimension in the case of H parameters. Some are having the dimension of resistance, conductance, some are dimensionless. And G parameters, it is I1 and V2. So here it is I1, V2 on the right side, here I1, V2 on the left hand side. So here V1, V2 are on the right hand side, and here V1 and V2 are on the left hand side. So that makes us our life simpler. So if they're asking y parameters and z parameters, you have to calculate only y parameters because z parameters are inverse of y parameters. Similarly, h parameters and g parameters are inverse. So if you calculate h parameters, you can directly calculate g parameters by doing the inverse of the matrix. You need not calculate all the parameters again. And we have seen that any network, if it is reciprocal, then z12 is z21, or y12 is y21, or h12 is minus h21, or g12 is minus g21. Then we have solved a few problems where they are asking whether the network is reciprocal. So then you have to calculate any one of the parameters and see whether this is satisfying or not. And then we have also seen, so in this question we have calculated H parameters. So if you see, for calculating H parameters, first you have to see, let us go back and see for calculating the H parameters. So if I make V2 equals to 0, I can calculate these two. If I make I1 equals to 0, then I can calculate these two. So you have to solve the circuit two times. One is V2 equals to 0, and another one I1 is equals to 0. So once you solve the circuit, I know that it is a little bit lengthy and it takes time, but that is the only way. You cannot skip it. You have to solve the circuit and you have to get the parameters. Once you get the parameters, you can check whether it is following the reciprocity or not by checking whether the condition is satisfied or not. So for different circuits, we have calculated different parameters. I will not go in detail, but the concept is the same. First, you have to write the equation and you have to see what needs to be made zero, whether V1 or I1 or V2 or I2, and accordingly you have to calculate the parameters, and then you will get the matrix. So once you get the matrix, you can check whether it is reciprocal or not. So again, there is less than a minute. So if this meeting ends, please join back. So that's all about two port networks. We have discussed about Z parameters, Y parameters, H parameters, and G parameters. And then we have also seen how to calculate different parameters for different network. The process is lengthy, I know, and there is a high tendency that you make mistakes. So please not make any mistake. So any doubts until week 7?
Yesterday I asked the problem. I had
Okay.
tried that problem. See, in the chat I have given a diagram. That V2 always seems to be zero. Is it like that? That four two terminals are directly connected by a short circuit.
Okay, let me check. Yeah, so you are saying this H parameters, right?
Yes, yes.
So what is your query in this?
The four to two terminals are directly connected by a short circuit here.
Okay, just a minute. Let me take it to my notepad so I can. So you are asked H parameters. Yeah. So now tell me what is your query?
See, at the port 2, there is a direct connection between the two terminals of the port 2 without any element.
Port 2, this port.
Uh,
Okay. There is no connection
Parallel to
because
V2, there is short circuit. So is V2 is 0?
No. Actually, that is the terminals that are there. So if you see, uh, like those are the two terminals. Now you have to excite it with the voltage or current that you need. Say here they are saying for calculating H11 and H21, you have to make V2 to be 0, and you have to calculate V1 and
Yes.
I1 and I2 and I1. So V1 by I1 and I2 by I1, that will give H11 and H21. So how do I make V2 0? I will make V2 0 by short circuiting it. So I have to short circuit it. So this I am making it externally. So once I have short circuited, I have to calculate V1, I have to calculate I1, I have to calculate I2. So once I calculate this, then I will do V1 by I1 and I2 by I1. Then I'll get H11 and H21. So this is the first step. So first you will short this and
But
calculate I1,
parallel to
I2
that
and
red
V1.
line, already there is a black line. So it is already, does it mean that already it is short circuited?
Okay, this line you are talking about.
Yes, yes.
Yes. It is already shorted, but I am not sure. I think there might be a mistake.
Yeah, but I couldn't solve the problem at all.
Okay, I
I
think there
calculated
might.
H11 and I calculated two parameters, but for the other H12, you have to
Yes.
calculate V1 by V2. Means that V2 is 0. I didn't know how to do it.
Yes. So here I1 is equals to 0, which means it is open circuit. So it is on the left hand side, it is open circuit. So this is open circuit. Then V1 is equals to, sorry, I1 is equals to 0. So when this is open circuit, then you have to calculate what is the voltage V2, I2, as
V1
well
by
as
V2.
V1.
But the
Yes.
terminals are parallel to a short circuit. So if we substitute V2 equal to 0,
V2 is 0. So I am not exactly sure whether this needs
then
to be there or
H12 will
not.
become infinity.
Yes. I'm not sure whether this will be there or not, but you have to check. Maybe it is there, but I'm not sure. If it is infinite, then the answer cannot be finite
Answer is,
value.
yes, answer is some finite answer.
Yes. So yeah, maybe they might have made a mistake. Maybe it is not there, or maybe there is some resistance. I'm not sure. It cannot be there. So either there will be a resistance here, or there will be no connection at all.
Yes.
Yeah, you are right. Okay. So after the two-port network, then we have discussed about the, sorry, then we have discussed about the op-amp. Yeah. So then we have discussed about the operational amplifier. So we have discussed what is op-amp and what is the negative feedback amplifier, how to decide whether the op-amp is in negative feedback or not. So for a given circuit, then we have seen how to calculate the gain from the input to output, and if it is non-ideal op-amp, then how to calculate. And we have solved many problems. And we have also seen this is one of the important topic, how to determine whether the amplifier is in negative feedback or not. We have seen that we have to remove the op-amp and excite it with a test voltage at V0, and then we have to see uh, that whether V positive terminal minus V negative terminal, whether it is negative or not. Accordingly, the terminals will be selected whether it is positive or negative. And we have solved many problems on that to check whether it is whether is it in negative feedback or not. And we also seen if there are multiple op-amps, how to determine. First, we'll calculate the terminals of one op-amp, and then we'll calculate the terminals of the other op-amp. By following the same procedure, we'll give test voltage, and then we'll see whether V positive terminal minus V negative terminal is coming less than 0 or not. And these are very interesting problems, and you should not make any mistakes. So if you have any doubt regarding this, I suggest you to go back and do it again, because this is like very important and very tricky question that you tend to make mistakes. So they might ask in the final exam. So you have to be very careful with these questions. And then we also see the power supply of op-amp, that the op-amp will have power supply, and it might get saturated if the input is not in this linear region. So only when the input is in this linear region, op-amp will act like an amplifier. If the input is on the other region, then the op-amp will be saturated to the power supply, which could be plus 12 and minus 12. So we have seen what should be the input so that the output will not get saturated. So we have seen a few problems on that. And in the week 9, we have slowly moved on to first order circuits and second order circuits eventually, and how to solve first order circuits and second order circuits. So in the week 9, we have discussed about first order circuits. First, we have got the differential equation, and then we have seen what is the generalized solution. We have written it as Vc of infinite plus Vc of 0 minus Vc of infinite into e to the power minus t by tau. So now for any first order circuit, now first we have to determine the time constant. We have to determine the initial condition. We have to determine the final condition and use the generalized solution expression. So for any voltage or current, this is the expression. And how will you find the VC infinite, IL infinite? Because in this week, it is only the DC input, not time varying input. So at final condition, capacitor will be open, inductor will be short initially. If they have not given any initial condition, then capacitor will be short, inductor will be open. But usually they will give the initial condition, the initial voltage. So there is no difficulty in that part. So for any given question, we have followed the same rules. So I have always copy pasted this and I have followed the same rules. First, you will find the time constant, then the initial condition, then the final condition, then use the generalized expression. So all the problems I have solved using the same steps. First, I have calculated the time constant, then I have calculated the initial condition and final condition, and then using the generalized expression. So all the problems may be somewhat little bit different or tricky. Sometimes they give the parameters, but the process remains the same. First, determine the time constant, then you have to determine the initial condition, then final condition, then use the generalized expression to get the solution for the inductor current. Here also it is the same. So for every question I have explicitly mentioned this so that you will follow the same steps and procedure whenever you solve this problem. So this week it is very simple and straightforward. So we have only discussed about first order circuits, but the entire week can be summarized in a single equation. So whether it could be voltage or current, say voltage VC or V of t is nothing but V of infinite plus V of 0 minus V of infinite into e to the power minus t by 2. Similarly for current. So you have to find the time constant, initial condition, final condition, and then use the generalized expression. And in
I
week
have
10,
doubt in
yes,
in capacitors. Always we assume that initially it is a short circuit and final steady state it is a open circuit.
yes,
But in some cases it is not like that. I want. I have
yes.
given one now. Where there is where like conditions like that will come. I want to know.
So initially, sometimes what happens is at t equals to 0. So in this question, if you see, there are two capacitors connected in
Yes.
series. So that is the border case. Let me go back to one of the problem that I have discussed. So here in this question also, this I have put star mark because this is a like an exception case. If the capacitors are connected in series. So at t equals to 0 only, the capacitors are directly connected in series with the voltage source. So now what happens is they will immediately get charged. So in order to satisfy KVL, they cannot be short circuited because then voltage source will be short circuited. So in this case, which is again an ideal case, what happens is capacitors will get charged in a fraction of a moment. And how they will get charged? Uh, Usually for resistors, if it is R1 and R2, you know that voltage across R1 will be R1 by R1 plus R2, and here R2 by R1 plus R2. Similarly for capacitors, the same. Voltage across C1 will be C2 by C1 plus C2, and voltage across C2 will be C1 by C1 plus C2 into 4 volts. So they get immediately charged. But will this happen in the like real life case? No, because if the voltage, there is a step function in the voltage, then current I is C into dV by dt. So there will be an impulse in the current. So huge current will flow. So which is uh, not actually feasible in the practical case because that much current cannot pass. So whenever there are two capacitors connected in series, then for calculating the initial condition, you have to understand that these capacitors will get immediately charged and like the voltage division happen similar to the resistors. So the voltage across this will be C2 by C1 plus C2 and voltage across C2 will be C1 by C1 plus C2. And that's how you get the voltage initial condition. Is that clear?
Yes, yes, yeah. All these are available in YouTube. These sums you have solved in YouTube.
Yes, yes,
It is
all are available in the YouTube, and these notes also I have uploaded in my drive, and the drive link is also shared, so you can access these notes
week
and
9.
everything.
Okay.
Roshan, I have not checked the Google discussion forum. I'm like still not yet fully recovered. I'm still like a little bit sick, so I'll check maybe in this weekend or by this weekend. I'll check somewhere. In week 10, we have discussed about first order circuits with time varying input. So in week 9, it is first order circuit with constant input. In week 10, it is first order circuit with time varying input. So in this circuit, what we have done is we have realized that it has two terms. One is the natural response, one is the forced response. So natural response, it is nothing but e to the power minus t by tau. So once you know tau, you can write it as some constant into e to the power minus t by tau. And forced response will be a scaled version of the forcing input. So now natural response, how will you get this constant? By substituting it in the natural response you will get from the initial condition, and forced response, how do you get? You substitute this equation in the differential equation, and then you will get this k1 and k2. So natural response unknowns will be obtained from the initial condition, and forced response unknowns will be obtained by substituting in the differential equation. So for any given question, first we have written it in terms of this equation. One is scaled version of the forcing input, another one is scaled version of e to the power minus t by tau. So one, using the initial condition, you will get one equation, and by substituting the solution in the differential equation, you will get another equation. So two equations, two unknowns, solve for it. So all the problems are same, and here also one exception case is there, because if the forcing input is same as e to the power minus t by tau, then the forced response will not be just scaled version, but it will be scaled version times uh, t time. Because if you actually solve the differential equation, you will get something like this. So when the forcing input is same as this decaying term e to the power minus t by tau, then the output or the Vc of t will be something like k1 into t by tau into e to the power minus t by tau plus this transient response term, which will remain the same. And again, you have to get one from the initial condition and another equation from the by substituting this expression in the differential equation. So here we have solved a different problems. One is RC, RL, and different type of network. And in every question, the method remains the same. First, you will write the generalized expression, and then you will get two equations, one from the initial condition and one from substituting the solution, and you will get two equations, two unknowns. And I know that these are a little bit lengthy, and you have to be very careful while solving. You should not make any mistake, because sometimes they ask for 2 marks only, but you have to solve the entire problem, and you have to solve these equations and get the coefficients and everything. If you make any mistake, you will lose the marks. But I know that these are very lengthy, but you have to do it, and you have to make sure all your calculations, everything are correct, else you will lose marks. So we have seen different type of problems, but the method remains same. So in the week 9, where we have discussed with the constant input, what will be the time varying voltage or the expression for voltage and current, we got the expression which is Vc of infinite plus Vc of 0 minus Vc of infinite into e to the power minus t by tau. And we have started with calculating time constant, followed by the initial condition, followed by the final value, and then substituting in the generalized expression. Whereas in the week 10, we have got that the expression will be scaled, some scaling factor times the forcing input plus some scaling factor times the decay term, which is e to the power minus t by tau. So first we have written the expression, then we have obtained the unknown values k1 and k2 by getting two equations, one equation from the initial condition and one equation by substituting this equation in the differential equation. So you need to get the differential equation as well, and then after substituting it, you will get it. So in the chat box, someone has mentioned, sir, need suggestion of preparation for final exams. Question will be mainly from the assignment of this year. Yes, question will be something similar to what they have given in the this what do I say, this assignment. So if you solve all the assignments and if you have thoroughly practiced this session, then you will know how to solve this uh, problems in the exam. So it will be something similar, and you can expect similar kind of problem. So please be thorough with the this what do I say, assignment. So you can expect similar kind of problems. So here they
We
have
do
given,
some
yeah,
with the
sorry,
cube. How to
sorry,
solve this sum with the cube?
cube. So each equivalent resistance between point A and B if each side of the cube is having a resistor R. Okay, so they are asking the equivalent resistance at this point. Okay, let us see how to solve A and B, right?
Yes.
So okay, give it a try. So they have resistor R here, R here, R here, R here, R here, R, 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 R. So they are asking what is the effective resistance between these two terminals. Say, because I cannot simplify this circuit, what I can do is, okay, let me draw. To connect the voltage source. So now I'm writing this as a resistor, 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 here also one resistor, 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 resistor. So now you have to basically calculate, say this is voltage is V test. You have to calculate this I
In
test.
parallel to the voltage source also there is one resistor.
One
Right?
resistor. So basically what we'll do is we'll apply KCL, KVL, and we'll get something like this, V test by I test, which will give us some R effective. Then in
Okay.
the question, whatever they are asking, R equivalent will be R effective parallel R.
Okay.
Okay. So now I'll just quickly go through week 11 and week 12 as these are discussed in the last this week and last week. So I'll just quickly summarize. So in week 11, we have discussed about the second order circuit, series RLC as well as parallel RLC. So in this week, we have first obtained the differential equation, and then we have generalized in terms of zeta omega n and omega n square, and then we have seen for series RLC uh, zeta is r by 2 into square root of c by l and omega n is 1 by root LC. And we have seen that how the damping factor affects the step response. For underdamped, how what will be the step response? For critically damped, what will be the step response? And for overdamped, what will be the step response? And here we have seen that depending upon the zeta, there will be different type of roots and the type of the response will change, and also how the solution will look like. And I have also given a table. You can refer to this table. And for parallel RLC, we have seen that zeta will be different. Although omega n remains the same, zeta will be different 1 by 2 r into square root of L by C. And then I have summarized the difference between series RLC and parallel RLC. These are the equations. And the only difference will be the zeta. So once the zeta is obtained, then you can know whether the roots are real and distinct or real and equal or complex conjugates. So for any given circuit, you have one transient response which will decay down and one forced response which will be there because it's the steady state response. So then sometimes we have to realize whether it is a series RLC or parallel RLC. And I have told that in order to check, first you have to remove all the voltage sources and current sources. Once you do that, you will know whether it is series RLC or parallel RLC. Once you know whether it is series or parallel, you can refer to this table and you can directly write this formula and you can directly calculate the zeta as well as omega, which will save you a lot of time. And if you see, if you they have given zeta and they have not given any value, using that formula you can get the value. So once you get the value, now you have to get the second order differential equation. So once you get the second order differential equation, now because they have given the steady state, what is the amplitude IR of t in the steady state, and they have given supply voltage to be 4 cos 10 to the power 80. So I know that IR of t will be some k into cos 10 to the power 80 plus 5. Now you back substitute it, you will get two equations, two unknowns, and you can solve it. Similarly, here they have given series RLC circuit. Why it is series RLC? If you remove the source, these two will be in parallel and it will be R, L, and C in series. So it will be series RLC. They're asking zeta and omega. I need not even write the differential equation. I can use the formula that I know to calculate zeta and omega. So most of the questions they are asking zeta and omega. So it is very simple and straightforward. But you have to understand that some of the circuits may not be completely series RLC or parallel RLC. In that case, you cannot do anything. You have to write the differential equation to get the zeta and omega. So in this question, you have to write the KVL, KCL and get the differential equation. Here I have not written it, but I have given an idea so that you can proceed further. And in V12, which is what we have discussed yesterday, it is all about steady state response using the phasor. So the generalized expression for the steady state we have written in a different way so that we can use phasors. So for resistance, the impedance will be R. For the capacitor, it will be 1 by j omega c. For inductor, it will be j omega n. And we have seen that for the given circuit can be converted into a circuit where everything is written in terms of phasors. So we'll solve the circuit in terms of phasors. Once we have solved in terms of phasor, then you can write I of t or V of t will be real part of that phasor into e to the power j omega t. From there, you will get the steady state expression. And we have also seen that complex numbers can be written in rectangular form or polar form. So polar form is widely used and it is also very easy to solve the problems using polar form. And I have said if it is cos, it will be angle 0. If it is sine, it will be angle minus 90 degrees. So please be careful with this. Sometimes the input will be sine, sometimes the input will be cos. So you have to be very, very careful. You should not make any mistake. And these are some doubts that we have discussed yesterday. So in this problem, if you see Vs of t is 6 cos, which means angle is 0. So I have put angle 0 and R is R. C is 1 by j omega c. Using phasors, I have calculated V0. Once I have calculated V0, then I have written the expression by writing real part of V0 into e to the power j omega t. So irrespective of the problem, the method remains same. Convert this circuit into phasors, solve the circuit in terms of phasors, then write the expression. So we have solved few problems. So if there are two sources, either you can apply superposition, but in this case, we have converted this into voltage source. Then both the voltage source can be realized using single voltage source. Then I have calculated the V0 bar, which is the voltage across the capacitors, and then I have done the same thing. In the question 4 also, same, it is RLC network, but here they have asked the Bode plot. So for Bode plot, we have considered three cases, and then we have calculated the magnitude, and we have calculated the phase, and we have drawn. And in the last question, it is a different type of network. They're asking the current, so I have calculated the net impedance using phasor, and then net phasor current is nothing but voltage by impedance. Once you get that, you can directly write the expression by writing this equation, real part of phasor into e to the power j omega t. And in the final problem, someone asked about the magnetic, the mutual inductance, and we have written the equation, and I think there is a mistake in the answer that they have given. So that's all the summary of the basic electrical circuits NPTEL course and what we have discussed in this 12-week session. Do you have any other doubts? If not, we can end this session here.
Okay, thank you.
So, sir,
Yeah.
sir, the answers there which are marked wrong.
Mhm.
So try, sir, please communicate with the
That is
authorities so that these they should be excluded
yes, yes,
because marks are getting
deducted.
down too much. Yes.
Yeah, I
Like
understood.
today we have also one submission and one question is already data is insufficient in the question.
Okay.
So
Yeah,
I don't
I
know how we have to guess.
Okay, okay, I'll check. As you have mentioned in the forum, actually I was not feeling well, so I did not check the forum. By this weekend, I'll check the forum and I'll forward it to the TS, corresponding TS and the course instructor to either give it like marks for everyone, or to exclude that question completely and not consider it for the grading. So I'll talk to the corresponding DS and I'll make sure that either marks will be given for everyone or it will be completely deducted from the grading. So
Okay, sir. Thank
yeah,
you.
yeah. Once you have mentioned in the forum, it's okay. I'll check and I'll forward it to the corresponding tools. Any other queries?
No, and while preparing for exam, if we have any doubt, can we mail to you?
Yes, yes. But I would
And if you
I suggest you
not
to mail me
format,
directly instead of sending it to forum, because as the course is
okay.
towards
I have
completion, we
noted
might
your
mention.
mail ID.
Okay, okay. Yeah. Then
Okay, thank you.
yeah. Okay, then we can end this session here. I wish you all the best for your exam. Do well, practice well, go through all the concepts. Don't miss any of the concepts. Solve all the problems on all the concepts. Then you will feel confident and you can answer the question in the exam. Similar type of questions can be expected in the exam. So solve all the assignment problems and you can expect the similar problems. Yeah, thank you. Thank you, everyone. Thank you for being interactive and I wish you all the best.
Thank you. Thank you very much.
Yeah. Okay,
Yes,
then
sir.
good night. Bye. This will be our last interaction. But if you have any doubts anytime in the future, you can always reach
Yeah.
out to me. And I'm again mentioning my email ID. So you can reach out to me. You can also follow me on LinkedIn. We can stay in touch. If you need any help in the future, I'll be there. Okay, then.
Thank you. Thank you for the support.
Yeah.
Thank you.
Yeah. Thank you. Good night.
Thank you, sir.
Thank you.